Richard always encouraged me to make interesting,
I just said
interesting
include the
slides.
conference logo.
So anyway, this is sort of of historical interest more than anything else. Like I say, one of the things I'm curious about is the old guys. What were the old guys thinking? And what was their thought process? So anyway, we're talking about number theory here, and we're talking about prime numbers. And we basically have three kinds of number theory practitioners. These are the real mathematicians. They use mostly algebraic properties of numbers because it turns out we're working on something called an integer domain. That's what our integers come from. And there are certain properties that go with that. For example, an integer domain is also a prime factorization domain. And so you have prime numbers. And then there's analytic number theory. That dates to the 19th century. And a guy named Riemann who created the Riemann zeta function. And analytic number theory it turns out is also connected intimately with the prime numbers. And then there's computational number theory, or what I would call conjectural number theory. That's us. We're the guys that like to fool around and do experiments and find out what might be true and what might not be true. And one of the things we have in our calculators, both the HP prime and the WP34, which I use a lot, both have a next prime function. So here's some historical milestones. Okay, at exactly 9 a.m. On 45th meridian time, October 23rd, 4004 BC. Okay, God created Adam according to the fundamental Biblists. And other fundamental Biblists believe that Adam's original language was Aramaic. Older languages like Sumerian that were not spoken by humans. They must have been monkeys or something. Now Aramaic has forms for the nouns that change according to number, just like modern Arabic. In modern Arabic, there's a singular and a plural, but there's also a dual. So, and I think we have somebody back there who just spoke before me and after me who may know that language. So now it turns so what you have is with the creation of Adam, immediately the first prime number was known, 2. Okay, and now the age of Pythagoras. Primes that are the sum of 2 squares. Those will become a subject of interesting study. Now, here's an experiment you can try on your calculator. Put in a complex number, put any complex integer into your calculator, and make sure that the real component is greater than the imaginary component. And square that number in complex and see what you get. Go ahead, somebody try it. Somebody try it. Try putting in, do 1, enter 2. We'll do 1, enter 2, and then hit complex square and see what comes up.
The real is.
What did you get?
Wait, the real is larger than the complex part?
Yeah, the real is the larger.
So we need 2 enter 1. So we need 2 space 1. Okay, squared. 3, comma 4.
3 and 4.
3 and 4. Yep.
Okay, try 1 and 3 and see what you get.
8 and 6.
8 and 6.
Yeah.
Okay, try 1 and 4 and see what you get.
15 and 8.
15 and
15,
8.
comma 8.
So if you notice, what you always get is, guess what? You get a Pythagorean triple. Did you know that?
I did not.
When you know that when you square a Gaussian integer, you always get a Pythagorean triple. So anyway, I guess this I don't know if this was known to Pythagoras, but it was certainly known by the time of this guy. Alexander the Great had conquered the world and established Greek thought everywhere, and Euclid compiled his Elements, and part of his Elements dealt with number theory, and Euclid knew that little fact about the Gaussian integers. Now, Eratosthenes was an interesting guy. He actually came from what is now Libya, and he moved to Egypt. He was very smart, and he caught the attention of the authorities and got a job in the library, and eventually was promoted by the pharaoh. The pharaoh's name was probably Ptolemy the 17th or something like that, because remember, Egypt was at that time under the rule of the Greeks. And one of the things he did was measure the circumference of the earth. He did that by measuring the length of shadows of vertical columns. And he knew the difference in latitude, so he was able to find out that the circumference of the earth was about 24,000 miles. And then anyway, time went on, and you had the Dark Ages. The German armies under Bohemond, sometimes Father Joe would call it the Holy Crusade. We would call it the Nachba, the first Nachba. But the Arabians resisted and maintained an Abbasid empire up until 1258, when the Mongolian army came through Baghdad and wiped the place out. But the Arabs were successful in preserving mathematical knowledge, and so you have Fibonacci, whose most important deed was not the Fibonacci series and the golden ratio. His most important deed was converting Europe from Roman numerals to Arabic numerals, which had a tremendous impact on financial accounting, among other things. Okay, go up to the 17th century. Everybody knows this one. I mean, for 350 years, people were trying to prove it, and nobody ever proved it. They tested up on computers up into the bazillions, and they never proved it until just a few years ago, and probably by methods unavailable to Fermat. So anyway, Pascal, of course, invented the triangle. A lot was going on in the 17th century because, among other things, astronomers were trying to do calculations, and the ancient Greek view of the heliocentric universe was wrong, and they realized it was wrong. Okay, now we go up here to some interesting unproven things. Goldbach, he he conjectures in 1740 that every even number greater than 2 is a sum of 2 primes. It's so obviously true. If you look at the possibilities, if you look at the possibilities, it's just so obviously true. It's been tested up in the bazillions, but yet it's never been proven. And then you have Legendre. He proved that he conjectured there's 1 prime between n squared and n plus 1 squared. That's something else. It's so obviously true, tested by computers up to the bazillion. Not just 1 prime. When you get up into the high numbers, there's millions of primes. There's millions of primes in there. But they still haven't been able to prove that there's even 1. Unproven after hundreds of years. Okay, here's Joseph Louis Lagrange. He was one of my favorite characters because one of his great accomplishments in life was that when he was in his 50s, he married a young woman who I think might have been in her late teens or early 20s, and he probably died with a smile on his face. And also, you notice he lived through interesting times and kept his head. Carl Gauss, he conjectured the prime number theorem. Okay, it was proved 100 years later by, among other people, a guy named Hadamard. But the prime number theorem has to do with the distribution of prime numbers. And we'll get into that in a moment. And then Riemann, creates the Riemann zeta function, which is this little guy here, which it turns out is related to the prime numbers by this formula. So the Riemann hypothesis, which has to do with the roots of this function along the x equals 1/2 axis, it's still unproven. Then Chebyshev discovered the Chebyshev bias. It turns out the prime numbers modulo 4 are more prevalent than prime numbers modulo that are 1 modulo. Let's see, the ones that are 1 modular 4 are more prevalent than they should be if they were truly random. Okay, now here's something related to the Lagrange thing. In 1845, conjectured 1 prime number between n and 2n. Well, once again, I mean, there's obviously, when you get up in the higher numbers, there's millions of primes in there, but nobody figured out how to prove it until years later, and it was Chebyshev, the Russian guy, that was able to prove it. So once again, there's the Lagrange thing again. So the thing is that there's a lot of things about primes that have remained unproven for hundreds of years. Even though they're obviously true, they should be easy to prove, but it just defies everybody. Okay, so communication systems. For example, here's an example of the Arecibo message, and they did send that back in the 1970s to M13, which is 25,000 light years away. So in 25,000 years, the aliens will come, and they'll come to do their usual to us. What is the usual? Well, you watch any science fiction movie will tell you it's the obvious. They want to do 2 things. They want to enslave us, and they want to take our women. Those are the things that aliens will want. Okay, And then there's a related to cryptography. So there was a movie made about prime numbers in cryptography. Okay, you see any mistakes in this? What's that? That's the sun. That's Mercury. That's Venus. That's Earth. That's Mars. Look, there's two big guys, Jupiter and Saturn. Uranus. Neptune. What's that?
Planet X.
What? There are no planets after Uranus. Pluto is no longer considered a planet.
But they said there's an invisible planet maybe still.
So that's a mistake. So anyway, we have this function in our calculators, next prime, and on a WP34, which is what I like to play with more than anything, the maximum prime you can get is that. That's a maximum prime, and if you go into double precision and integer mode, you can get a little bit higher. And the HP prime takes a while to compute the next prime. There's 10 to the 2000. I think running the emulator on my cell phone. I think it took about 20 minutes. But still, I mean, this. You had guys like Carl Gauss as a teenager was computing prime numbers up into the millions. This is way beyond the millions. This is a 2,000 digit number. That's more than Gauss could write down. So we have in our hands. Everybody here has in his hands great powers to do computational number theory and to do exploration and to be curious about these things that was not available in the classical mathematicians. And
Are there tables of prime numbers, all the prime numbers up to a certain number, and what is that?
Okay, Richard is asking how many primes up to a certain number, and we call that the pi function. And it turns out from the prime number theorem that was proposed by Gauss and proved by Hadamard, we know how to estimate that. And I'll show you that in a moment. Now I went online to a mathematics forum, and somebody posted a question. How can I calculate the next prime? And all of the answers dealt with the sieve of Eratosthenes. Now Eratosthenes was a great guy for measuring the circumference of the Earth, but to use his sieve for very large numbers,
It's impossible.
it's just not workable at all. You need something that goes faster. As I say, here, the sun will go out before that can happen. So I looked at the next prime that's in my calculator, and I tried it in different modes, and I found out that in integer mode it's somewhat faster, and this tells you how long it takes to do. This is how long it takes to do 10,000 next prime operations, according to where you start. So if you start at 10 to the 18th, it takes 350 ticks to do 10,000 of them. Now, 10 to the 18th, even that's a little bit above the territory where Gauss would be working. Gauss, I think Gauss quit at about 10 to the, I think 10 to the 7th was beyond him. But we're already at 10 to the 18th. Our computational powers are mind-boggling compared to what they had back in the 19th century. So we could be exploring things that the ancient people never knew about. So here's some functions related to prime numbers. Pi of n, the number of primes less than or equal to n that Richard just asked about. The prime gap, that's the gap between successive primes. The Goldbach function, okay? The Goldbach function is, as we said, Goldbach surmised that every even number is a sum of two primes, and the Goldbach function is a number of different ways, the number of different ways you can create that even number out of the two primes. So all these things are easily explored. So here I evaluated pi of n, and this shows how long it takes to evaluate it. Here's some I did not evaluate. However, this is an approximation. This is an approximation for the pi number, and it turns out this is called the logarithmic integral, and this is supposedly an even better approximation. So if you get down here, you see it's 576. Over here it's 576, but the Gauss approximation is not quite as accurate. It's in the ballpark, but it's not as accurate. On the other hand, this is a lot easier to calculate. And I did not. I quit before I completed this chart. So this will give you an idea of the time involved. But we can get up to some kind of big numbers. So here's the code for creating the prime gap function. I mean, that doesn't look so bad, does it? It just tells you how far it is to the next prime. Easy. And what makes it easy is the fact that this guy is built into the calculator.
Which calculator?
Now the Goldbach function, that's a number of prime pairs that add up to an even number. Okay, so here's some examples. 14 equals 3 plus 11, but it also equals 7 plus 7. So the Goldbach function of 14 is 2. Now, it turns out for larger numbers, the Goldbach function goes up into the millions. But remember, they've never even been able to prove that it's equal to 1. They never proved that it's greater than 0, but it's up in the millions. It should be easy to prove, you would think. Nope, not yet. So we have these unsolved problems, some of which are hundreds of years old, and so here's my variant of the Goldbach function, of Goldbach's conjecture. I say for an even number greater than 12, the Goldbach function is greater than or equal to 2. And if the even number is greater than 68, I say it's greater than 3. Then I have my conjecture number 2 is that there's something funny about the values that it never gets back to, like 68, 14, and 68, and all the other numbers that are at the bottom of the envelope of the curve have something in common. So That's the question. Why can't they prove it? It's been around for hundreds of years, and people have looked at it and tried. So anyway, I look at the lower limits of these functions, and you'll see that these numbers all seem to have something in common, except for that one, of course. Let's skip that one. Uh-oh. The interesting stuff is when you try to find the Riemann function of complex numbers, which unfortunately in my WP34 it's real numbers only. So anyway, I found this in my numerical in my number theory book. Many these problems have eluded centuries eluded solution for centuries. Attempts to solve such problems are often time-consuming and futile, but it doesn't mean you don't learn anything. So just imagine if you could go back into the 17th century and encounter guys like Fermat and Pascal and Goldbach and some of those old guys. You would have to, of course, you'd have to evade the Holy Inquisition because you would be considered a demon. But if you had your calculator, you could probably spend 15 minutes with them and advance number theory by centuries. Okay, we have better tools. Now, before I go to this statement, I want to mention Fermat's little theorem. Okay, this is a test for a composite number. If P is a prime number, any number A, any integer A to the P power equals A modulo P. That's an absolute test for a composite number. And the way it is used to check for primes, of course, is to find out if A to the P equals A modulo P, they say then P must be prime. Well, not necessarily. When we do that test, we say that A, the number that we're raising to the power, we say A is a witness. Now, if A to the P is not equal to A, we say that A is a witness that P is not prime. P is composite, and it's absolutely true. But sometimes A to the P does equal A modulo P, but P is not prime. And then what we say is that A is a liar. And so the way we get around that is to be sure we try a different value of A. Now I did lots of experiments and I found out that the most productive, if you're going to only check and raise only one number to the P power, the easiest, the most productive number you can use is 2. But to back it up and to be absolutely sure, try some other number like 3. Well, it turns out, what if you try every possible number? Try every possible number from 2 up to P minus 1. Believe it or not, there's some numbers that for which all of the possible witnesses are liars. And those are called Carmichael numbers. Now the first Carmichael number you'll find is 561. Well, if you look at it, let's see, 6 and 5 is 11 and 1 is 12. So add the sum of the digits. So it's obviously divisible by 3. And if you look at the middle digit, it's the sum of the first and the last digit. So it's also divisible by 11. So among other things, it's divisible by 11 and it's divisible by 11 and 3. So that's a Carmichael numbers. But as you get up higher and higher, the Carmichaels become incredibly rare, much rarer than the primes. And this is a very good test. And there's other tests that are based on this that avoid the problem of Carmichael numbers. One of them it's called the Miller-Rabin test. If you're interested in testing for primes, look up the Miller-Rabin test. It's actually not that hard to program, although I haven't done it yet myself. I've just been working with the Fermat test. But if you want to play with prime numbers, if you're a curious person, go do it, is all I can say. Now you can wake up.